We are waiting for his presentation. Okay. Let's start.
All right, perfect. So am I able to control this somehow? There we go. I see everything. Perfect. Okay, so I'll share my video just for a second, just to say hi to everybody. Perfect. All right, well, hi everyone. My name is Jeremy, for those of you who haven't met. Thank you very much for the invitation to speak with you all today. But yeah, to save bandwidth, maybe I'll turn my webcam off for the most of the presentation. So as promised, in the next 30 minutes or so, I'll try to give a mini crash course on star clusters and then discuss how they're currently being used in the age of large-scale surveys. Now, star clusters themselves come in all sizes, but to give you an idea of what these things really look like, if you're not super familiar with the field, you can look at a simulation or a snapshot from a simulation. Oh, is that? There we go. Of a massive star cluster. And so what should really draw your eye here is this kind of white square, or white cube. So one side of this box is 4 light years, which is roughly the distance to the star closest to the sun. So in a volume where locally around us there's only 2 stars, star clusters have tens to hundreds of thousands of stars. They're gravitationally bound to each other and orbit their own center of mass, which then orbits the center of a galaxy. And they play an important role in the universe, and simply because they're everywhere. We see them in spiral galaxies like our own. This image here is showing kind of a map or the locations of 119 of the 150 known globular clusters in the Milky Way. So we see them not just in the Milky Way, but in all spiral galaxies. We even see them in dwarf galaxies or satellites that are going around the Milky Way. So for example, here I'm showing the Fornax dwarf galaxy, and even small dwarf galaxies have 5 or 6 globular clusters or star clusters orbiting within them. And then even elliptical galaxies have upwards of 10,000 star clusters. So here's an image of M87 at the center of the Virgo cluster. And due to the distance of M87, almost every point-like object you see here is a star cluster. And so, like I said, some of these can get up to greater than 10,000 star clusters in number in a given galaxy. So the fact that we see them in all types of galaxies suggests they play a pivotal role in the galaxy formation process. And it turns out that the formation and evolution of star clusters actually goes hand in hand with their host galaxy. So stars, we know, don't actually form alone. They form in a clustered environment, which means when giant molecular clouds collapse to form a single star, or they don't collapse to form a single star, they actually fragment and can form anywhere between several tens to several millions of stars, depending on the mass and size of the cloud. Now, the exact formation process for really high mass star clusters isn't really well understood, so we can continue to study regions of active star formation and also try to rewind the evolution of observed clusters to constrain how they form. Now, what separates a star cluster from, say, a dwarf galaxy or a low-mass galaxy is that they don't form within a dark matter overdensity, which means they must be forming in regions where there's dense, high-pressure molecular clouds. Perhaps they need a galaxy merger to trigger that formation. We also believe that a certain fraction of even the Milky Way's star cluster population has been accreted, didn't necessarily form within the Milky Way. And these regions are typically less than 100 parsecs in size, with most of their mass squished into the central few parsecs. Now, since stars have been forming in a given galaxy since the galaxy itself was born, star clusters can be used as tools to study their host environment. Sorry, I don't know if it's on everyone's end, but there's a little bit of lag every time I change slides, so that's why I'm pausing so much. So let's piece together kind of a star cluster roadmap of a galaxy, if you will. So as a galaxy forms, as do star clusters, they're usually the very first things to start forming in a galaxy. And they can be very roughly split into two types: high mass, dense clusters, and really low mass, extended clusters. Now, and they don't just sit there and hang out for the next 12 billion years or so. They have a very complex evolution, long list of internal processes. You have individual stars undergoing evolution, two-body interactions between stars, binaries, triples, quadruple body interactions, and they're even dense enough to have collisions. They're not in isolation, right? They're inside an external galaxy, so they're subject to a gravitational field which can strip stars, inject energy, both over long and short time scales into the cluster. And their dynamical history complex as well, if they're in a accreted star cluster or they've experienced some sort of merger event, which can be pretty interesting. And then so between formation and present day, you kind of get these high and low mass clusters separate even further. So the very high mass ones that formed right at the same time as the host galaxy, they're typically able to survive to present day. They form at early times and live 10 to 12 billion years, so we can observe them today. These ones are what you typically see in the literature as globular clusters. But the low mass clusters that formed when a galaxy was first forming will dissolve pretty quickly, on the order of a few billion years. So any low mass clusters that you see today, you know that they formed relatively recently, because their dissolution time is so short. So bringing this back, must be the images in the slides. All right, so bringing this back to our roadmap, when the galaxy is first forming, stars are also forming in a cluster with a range of masses and densities. The most massive ones survive to present day, so they can tell us a lot about the current and past structure of a galaxy. And then the low mass ones, since they either most recently formed, so they can tell us about star formation, or the ones that dissolve and break up, they do so in the form of a stellar stream. So these large streams of co-moving stars across the sky are kind of what's left of a disrupted star cluster. And they can be used to tell us about galaxy structure as well. And so for both types of clusters, whether it's high mass, low mass, or a stellar stream, large-scale surveys tell us a lot about them. And that's whether it's a Hubble Space Telescope, which has had for a long time now dedicated time to go around and observe every high mass star cluster in our galaxy, or even more large scale than that, things like Gaia and Apogee, which are able to give us structural properties, kinematic properties, chemical abundance properties of all these stars. It's a huge wealth of data that we're really just now diving into. And we get this for both star clusters and their remnants. So on the left here is a few different plots showing the positions of stars in the famous GD1 stellar stream extracted from Gaia, with the bottom plot marking kind of a number density profile along the stream. And then on the right is a simulation from Ray Carlberg in 2018 showing that since star clusters were forming in a galaxy over time, and it's been accreting other galaxies and other star clusters over time, you really expect a galaxy to be full of stellar streams. Unfortunately, they're often pretty low density, so there are a few other well-known ones. It's hard to pick out photometrically just by eye that a stream exists. And you really need to know things like the kinematics of individual stars and even their chemistry to identify it as a stream. Because within a star cluster, there's a very narrow range of chemical abundances between stars. So if you see a group of co-moving stars with similar abundances, it's a safe bet that they formed together. And so having all these surveys and all this wealth of information, we can really effectively start using clusters as tools to study the universe. I'm going to just talk about a few ways in which we can do that in my next few slides. Now, some common common statements that you'll see in papers, proposals, presentations on star clusters, including my own, are that all stars form in clusters, all galaxies have star clusters, and star clusters can be used as tools to study their host galaxy. They're cluster people really trying to sell you that star clusters are the most important thing to study in astronomy, and nothing else matters. But really, only one of those statements do we know for sure, in that all galaxies have star clusters. The other two, I think they're open questions. So I think I more accurately said a few slides ago that all stars form in clustered environments, because I think that has a range of definitions. Stars, if they just form with 10 or even 50 other stars around them, I'm not sure we would define that as a star cluster. That's more like a loosely bound association that quickly breaks up. And then the ability to use star clusters as tools to study their host galaxies is a general statement that's said a lot, and it's said by myself as well. But until we understand clusters themselves through and through, there's always going to be a wide range of uncertainty to any conclusion you make about a galaxy using its star cluster population. And so I'm trying to kind of merge those two things together, both understand star clusters better and really understand how we can use them as tools to study galaxies. And so to deal with those two open questions, I think the most reasonable place is to start with our sun. It's one of probably the best, most well-studied star in the universe, and we can start there. So if our sun formed in a cluster, there's already a few constraints we can place on it. So just by the mere fact that we have a planetary system intact, you can place the constraints that this host star cluster we formed in couldn't have been more than 800 solar masses with a half mass radius or effective radius of 3 parsecs. Any more massive or any denser than that, it's very hard for a solar system to survive. And then in order for life to develop, that star cluster must disperse within a few million years, simply because if too many supernovae events happen, there's a good chance we're bombarded with radiation to the point where life cannot develop. So what likely happened is that our sun formed in an unbound or even loosely bound group of stars. So not technically a cluster, but still it didn't form alone. It formed with other stars around it. And a reasonable question to ask is, well, where are those stars now? And to answer that question, I'm going to take a quick mini tour of our galaxy. And I mean very, very mini. So the familiar picture is that the Milky Way is made up of a stellar bulge, a stellar and gaseous disk, a stellar halo, and then a dark matter halo. And the evolution of a star cluster and then the evolution of stars after they escape a star cluster is very sensitive to these components. And we all know you can even dig deeper than that, because there is, gas, which I haven't really talked about, baryonic substructure, so things like giant molecular clouds, other star clusters, spiral arms, a bar, and there's also potentially dark matter substructure, whether you're talking about large satellites going around the Milky Way or some population of lower mass subhalos going around the galaxy. And so what we can do is run simulations of star cluster evolution to determine how each of these factors could have disrupted the sun's birth cluster. And so what I'm showing here in this picture, this is just kind of a top-down view of the present-day distribution of stars that formed in a potential star cluster that hosted the sun. So it follows those initial constraints I highlighted a few slides ago. I may put one at the low density end and one at the high density end and let it run for 5.5 billion years, the age of the sun. And there's different models here. So there's a static model that's just analytic, bulge, disk, and halo. There's galaxy models that include a bar and a couple different types of spiral prescriptions for spiral arms. And you can see, depending on the galaxy model you adapt, the stars that escape the cluster that the sun formed in are either nicely distributed in kind of a thin stream around the galaxy, or can be completely broken up and spread out with anywhere within 10 kiloparsecs of the galactic center. And then while I haven't tested all forms of substructure, we've also done a test of what giant molecular clouds will tell us. And as you can maybe naively expect, having GMCs running around your galaxy model potentially serves as a source of energy injection, both to a star cluster as it's disrupting and stars after they have escaped. And so you can have stars that all formed in the same cluster very quickly be redistributed throughout the Milky Way. One interesting conclusion from this study was that spiral arms in particular can really destroy star clusters that form and evolve in the plane of the disk and really spread out all those siblings. So having run simulations like that, the idea is then to go through, take advantage of these large-scale surveys, and try to find them all. Find other stars that potentially formed with the sun. Let's confirm this idea of stars forming together and how they've subsequently evolved in the galaxy. And so Gaia gives us the bulk of the information that we need, positions and proper motions of over 1 billion stars. Then you throw an apogee that gives you spectra for over 200,000 stars. You now have a very large parameter space that you can really use to qualify and quantify every given star in the data set. So combining Gaia and apogee together, you have the composition orbits of over 200,000 stars. If you just look at their chemical composition, so here's just looking at metallicity, you can see that there's about 19,000 stars in this data set with near solar metallicities. Note in this image, solar metallicity is not at 0. This has to do with how apogee calibrates metallicities. So the solar metallicity in this case is a little over 0.06. And then if we extend that to other abundances, aluminum, sodium, things like that, I think we used 7 or 8 different abundances. You can pare that down to about 9,500 stars, which chemically speaking are consistent with being born in the same cluster or association as the sun. But we have more information than just chemistry. You can look at the orbits of these individual stars. More specifically, we look at orbital actions. If you're not familiar with orbital actions, that's okay. I've kind of changed my axis here to just show that you're probing either radial motion, motion away from the disk, or motion around the galactic center. And that at least is angular momentum, which most people should be familiar with. And on this plot, I'm showing the sun's location relative to everything else in our data set. Which means now we kind of have a whole built-up catalog of stars with similar orbits and similar chemistry to the sun. And so I'm trying to plot all those here just in 2 different plots. These are, again, orbital actions, but I'm showing them just with their qualitative definitions. And in blue, I'm showing the results of those simulations, both in the static galaxy model with just an analytic bulge disk and halo, and then these non-static galaxy models with GMCs, spiral arms, and a bar. The simulations are in blue, and then observations of not all stars in our catalog, just ones that are near our simulated data, are overplotted in orange. The sun's values are essentially at the very center of those distributions on the left in the static galaxy model. So we have at least one observed star that is very close to the sun in chemistry space and in kinematic space. Almost 500 additional stars that you could associate with the sun, chemically and kinematically, but those depend on the galaxy model that you assume. And you would have to run, I think, a large suite of simulations to attach some sort of uncertainty or probability estimate of those being siblings, because different realization of your GMC population, our alarm properties would change whether or not you would associate a star with the sun's birth cluster or not. But I think the fact that we found at least one was pretty exciting. Which we dubbed solar sibling number 1, only 360 parsecs away. nearly identical chemical composition as the sun across many elements. So I've showed the 7 elements that we used there. And orbit consistent with being ejected from a dissolving solar cluster in all of our galaxy models. No assumption had to be made about GMCs, spiral arms, or anything like that. In every case, it overlapped with the simulated data. And then, like I said, to confirm any more solar siblings, I think we really need to narrow down the galaxy model that we use. But if you take this as evidence that the sun did form with other stars, it's just kind of loosely confirming this statement that stars don't form alone, you can actually start finding other siblings, not just solar siblings. And this is something we did with a very recent paper by Natalie Price-Jones that just came out a few weeks ago. And so here I'm showing roughly 150 stars that we found could be split up in the same catalog, that could be split up between roughly 10 different groups. So what I mean by that is that of these 150 stars, they're in groups of 15 with which we believe they all formed in the same cluster. Sorry, the 15 stars formed in the same cluster, and then another group of 15 formed in their own unique cluster. I'm showing all the stars in orange, but the blue triangles, red squares, and red pentagons are specifically showing stars that we consider to have formed in the same star cluster. And we also show the age of those stars, which is also consistent with them forming at the exact same time. So you're actually piecing together the star cluster formation of the Milky Way here and finding stars that form together, and they're all spread out throughout the galaxy. And it's very important to highlight, though, that chemistry or kinematics alone are not enough of a smoking gun to believe 2 stars are siblings. You really need both. And even then, you can't really rule out yet that 2 stars formed with the same chemistry and escaped from the same cluster, but ended up on similar orbits without significantly constraining the galaxy model. So there's more work to come here, but I think stars that don't require too many fine-tuning of the galaxy model together and helping us piece together the cluster formation history of the Milky Way. Now, those stars that I showed before aren't even in streams. There's no obvious stream connection between these groups, so the stream has already completely dissolved. But there's this intermediate stage between star cluster and stars spread out throughout a galaxy where things show up as streams. And so the second thing, or I guess the last thing I wanted to talk about, is whether streams can tell us even more about the galaxy in which we live. So there we go. So like I said, when stars escape a star cluster, they initially populate tidal tails, like you see the famous Pal 5 tidal tails here. And then once the progenitor, the cluster itself, dissolves, you're just left with a stream. Now these are very useful for tracing orbits of stars and of clusters in general, because they're very sensitive to them, and they're very sensitive to the microscopic properties of a host galaxy. So substructure of any kind can imprint as properties on the tail or the stream. For example, any gaps and underdensities along a tidal tail or a stream can be caused by substructure. And people have used this to constrain the properties of GMCs and dark matter subhalos in the Milky Way. And the stream I showed earlier is the famous GD1 stream from Gaia DR2. In this particular case, it was cross-matched with pan-stars, which had a better photometry. And now if we want to use streams to understand galaxies, we need to know how they form. So we also recently simulated a large suite of star cluster simulations to try to reproduce the exact GD1 stream. So this is probably a little more zoomed out than it should be. But for our large suite of simulations, so range of initial stars, numbers, sizes, and masses, we really tried to reproduce the length of the stream and the location of one of the locations of the progenitor of the stream. So GD1 has fully disrupted, but we looked for, there's a few different proposed locations of where that progenitor could be based on gaps and underdensities in the stream. And so we came up with a model that that really reproduced the properties of GD1 very well, and it suggested that The stream itself has a dynamical age of about 3.5 billion years, potentially indicating a time that it was accreted by the Milky Way. And for no reason that I've really explained or I've come up with, is that this is very similar to the believed dynamical age of Pal 5's tails. They're not causally connected or anything like that, but it could point towards both the GD1 progenitor and Pal 5 being accreted from the exact same event, which I think would be a very interesting thing to follow up on. And so what this is all working towards, with chemical information of star clusters and streams, Dietrich Krusen had a paper recently where he was able to combine all that information and putting together the history of
We have almost 5 minutes.
Okay. Oh, thank you very much. I really just have like probably 2 more slides, so I'm on time. So able to combine all this information and piece together the merger history of the Milky Way. And he kind of broke up different star clusters into different merger events. You can also do things like constrain the mass profile of the Milky Way if you have cluster kinematics. And then I think if we keep finding stellar siblings, keep finding more streams, you can really refine the full Hubble time evolution of the Milky Way with these surveys. So just ending here with my conclusions. Hopefully I've clearly shown you that star clusters can constrain things like GMCs and the substructure of any kind in the Milky Way. And we can use that to confirm that stars don't form alone, and we can even find some stars that form together. But since these studies are so sensitive on the details of the Milky Way, you can kind of flip that around and use the properties of these siblings and their distribution to constrain things like the bar and spiral arms of a Milky Way. And ultimately, what we're working towards is being able to rewind the dynamical clocks of star clusters, which will then in turn allow us to rewind the dynamical clock of the Milky Way. So that's brings me to the end of my talk, maybe a few minutes early, but leaves lots of time for questions. So thank you.
Thank you so much for your interesting talks. We have enough time for several questions. The first one is Hossein Shanavar. You may see in the public chat buttons.
Yes, 200,000 stars around the sun. Yeah, so Apogee's, the whole Apogee survey, which I wish I had a screenshot of its imprint. Yeah, so that's 200,000 stars with the sun roughly at the center of that survey. So they're all nearby. And so we've limited ourselves statistically to just looking for stars around the sun.
Okay.
The first question.
Hossein Haqi, you may start asking your question.
Hello, Jeremy.
Hi.
Nice to see you. Yeah. Thank you very much for an interesting talk. I have a question. So you think that in principle it is possible to trace back the sun to find its progenitor cluster by, for example, dynamical analysis or taking a look at the composition? Yes.
I do, but I'll throw in the caveat there that I still think we need to find a way to quantify some probability, because I think there's a decent chance that a star cluster somewhere else in the galaxy with almost identical chemical properties that formed at the same time, a star could be kicked out of that one and still end up on a comparable orbit to the sun. So I think you need some really large suites of simulations to throw some probability to that. But I think in principle it is possible.
Yeah, but because I don't know why, but I think it is very hard to believe that this can be possible, because, for example, if sun is escaped few giga-years ago from a cluster, it will mix with other stars in phase space, unless it is, it has been escaped very recently from star cluster.
Right. So, and that's kind of, I guess, what we're trying to do is really put a box around that phase space. What's the biggest possible phase space the sun could, or any siblings could fill and still be siblings? And then, so I think that's kind of what we've done so far. And I think then what you need to do next is see how much different phase spaces from different birth clusters can overlap. And that's probably where you're going with. If they overlap a lot, then the probability of saying 100% these two stars are siblings is probably pretty low. But isn't that bad. I think it opens the door to being able to say with a bit stronger conclusion.
There is another question by Pavel Krupa. You may read it.
Oh, let me scroll down.
Pavel, you can turn on your microphone if you like.
Yeah.
Okay, yeah, I can. Can you hear me?
Yeah.
Pavel.
Yeah, good. Okay, so the question was on the overdensities and underdensities in the tidal tails. It has been, Jeremy, you said that it's because of subhalos or substructure punching through the tails, but the work of Andreas Cooper has shown that these are overdensities, epicyclic overdensities, but you didn't mention that. So do you discard that possibility?
Thanks for asking that question. And I usually bring up Andreas's work and highlight that when I'm talking about streams in a bit more detail. So absolutely, as you said, that the natural way stars escape star clusters leads to these over and under densities, and there has to be over and under densities above and beyond what to substructure interactions, and that requires doing some sort of like complex Fourier analysis of your stream to determine whether you're seeing more underdensities than the natural escape would produce. So thanks for highlighting that, Pavel, because that's a very, very important point.
Any other question?
There was one question: based on observations, do we expect particular dark matter substructures around star clusters? Is there any specific correlation between the two? Right, so substructure, so believing kind of cosmological dark matter only simulations, the substructure fraction is pretty low in the Milky Way, so it's probably 0.1% around the solar circle, getting up to maybe 3% in the outskirts, in the outer halo. So I think where you're most likely going to see substructure star cluster interactions are going to be ones at large galactocentric distances. And that's maybe the best chance you have of seeing substructure interacting with star clusters entitled in stellar streams. In the inner regions, I think the substructure fraction is pretty low, although there's been arguments that at least one substructure dark matter subhalo has interacted with the GD1 stream, which I think is within 20 kpc. But that's probably a rare event, though, in most cases.
Okay, thank you. Another question by Mehdi Amiri.
Are these stars satisfy the Tully-Fisher relation? Sorry, which stars are you referring to?